Hi, gang. Welcome to Computer Graphics. We're coming into the home stretch now. We have a lecture today and a lecture on Monday on ray tracing, and that'll bring us into the home stretch. So we have 2 more lectures, and then we have 2 days of project presentations, and that'll pretty much bring us to the end of the quarter. So we're coming into the home stretch. So as I said, today and Monday, we will look at ray tracing. So let me bring up my notes here. One little bit of business before I bring up my notes. For those of you, because of weather, I gave program extensions. There's a link that's already up to a new sign-in sheet. The sign-ups, code walkthroughs will be Monday afternoon. So that's different. We've done all of ours on Tuesday, Thursday, so I don't know if you guys have different kind of schedules, but it's up there now. And if you've got some constraints on your schedule, I encourage you to rush over there right now and get a slot. Just go to Moodle and under assignments, there's assignment 4 extension sign up, and there's also assignment 5, the ray tracing assignment that we'll talk about here in just a little bit. But you can go ahead and sign up, Landon, at OWL, as they say. Okay. So with that bit out of the way, so we're going to today talk about ray tracing. Ray tracing is the most comprehensive illumination reflection model in computer science, or in computer graphics. It uses the Phong illumination reflection model, but it extends that model rather dramatically. And this is similar to the kind of image that you're going to create on assignment 5. And at first thing is it looks very pretty, right? We have a checkerboard here, some sky in the background. We've got a lighting source. You can tell that, like all of our lighting sources I can do in this class, it's over your right shoulder, right? The light source is behind you over your right shoulder as you're looking at the scene. And you can see we've got a slightly bluish tinted ball, a slightly greenish tinted ball, a yellowish tinted ball. They're highly reflective. You got specular highlights on them. The specular highlights are coming from the Phong illumination model that we're used to. But what we're not used to is I've got reflections here. Like in the goldish yellow ball, I can see reflections of my other 2 balls, right? And in my greenish ball here, I can see a reflection of this sphere, and I can see a reflection of this sphere. And if I go over to the bluish ball, I can see the greenish sphere, and I can see this one. So I can see reflections in my spheres. So if I look at my checkerboard has reflections of these spheres. The reflection of this one is probably out here in front and it's been cut off. Another thing is you have shadows of the objects here. I do note that the shadows don't seem to be reflected. Isn't that kind of interesting? But the level of realism here is far, far more than anything that we've done so far. And so this is essentially your assignment 5. I'm not going to have you do this. This is actually a glass ball that you can see through. So it's not reflecting, it's actually bending and refracting the light that's passing through it. So we're not going to do a refraction sphere, but we will do a number of highly reflected spheres. We will also have a checkerboard, and we will, so basically you will implement something that looks pretty much just like this, except it won't have a transmissive sphere. Yeah. Andrew goes, wow, when I'm saying how pretty it is, and then he's scared when I tell him that he's going to implement it. I find that pretty funny. I also find it sad that a third of the class isn't here to listen to the lecture. And yes, Landon, that is unfortunate that computers do tend to burst into flames when we implement ray tracing. That is kind of the negative there. So as Landon is beginning to worry, it is highly computationally expensive. Okay. By the way, this one I want to give credit where credit's due. I didn't actually program that particular image that I showed here. That was a student of mine a couple of years ago, Hunter Anderson, did this, and he went and on the one that I gave him, shadows weren't required, and I didn't require a transmissive sphere, but he wanted to go ahead and impress me, so he added a glass sphere to it, and I was like, okay, that one's cool. I'm going to save it. So how does ray tracing work? Well, ray tracing works backwards. You trace rays, but instead of tracing rays from a light source through an environment and the objects it hit and where the rays eventually end up, you actually trace the rays backwards. We pretend that the rays are shooting out of our eyeballs through the pixels of the screen. Now that seems a little weird because we don't have little laser beams behind our eyeballs, right? But think of it that way. And it works out. Why? Well, let's say we ran it forward the way physics really works, right? With the light rays coming out of light sources and hitting things. What do you actually see? Well, you actually see the light rays that end up hitting your eye, right? So all of those other light rays that landed on all those other surfaces would just be wasted computation. So by running the process backwards from your eyeball, the center of projection, 0, 0, minus 500 is what we've been using, right? By running the process backwards from your eyeball through the environment to the light sources, you'll end up with the same thing in the end that hits your eye, but you're only doing those light rays that end up hitting your eye. Does that make sense? Any questions about that? So that's the first thing. It runs backwards from the way light rays run in the real world. So what we do is you imagine the screen as, well, like what it is. It's a bunch of pixels. And so you imagine a light ray going from your eye through a pixel in the screen into the environment. And then we trace where that light ray hits, where it's reflected, where it's refracted, and then for each of the reflected and refracted rays, we look at where they hit and what the reflections and refractions are for those rays, et cetera, until we reach some depth where we throw up our hands and say, I've gone deep enough. I don't want to go any further. I'm scared. So that's how this works. So if a light ray, when tracing a light ray, if it doesn't hit anything, you just make it the color of the sky. So like these rays up here, right, each pixel again is a ray. Each pixel represents a ray. So all of these things up here, they didn't hit anything, so they just got set to the sky dome color of light blue here. Okay. Sometimes if we look at like over in this region here, a light ray hit the plane and then bounced off in some direction but didn't hit anything else. So in that case, not a lot of work happens. You hit the surface and then you bounce off and hit the sky. That's the reason the white here is not quite white, because it's got a little bit of this blue from the things that went off and hit the sky dome, right? But sometimes if you have a ray that like goes and hits here, well then that light ray hits here, bounces and hits this ball here, and then actually if you look really, really careful, you can see the reflection of the reflection, the original sphere in this thing if you get really close. Now yes, it's a lot smaller and dimmer, but the light ray hit this ball, hit this one, and then bounced back. And it's all there, right? So, and in fact, if you imagine two mirrors, you could have, you know, the infinite mirror effect here. Now, obviously, you can't go infinitely deep, but that's what's happening. So we're tracing the rays backwards from your eyeball into the environment and looking at what it hits. Some rays just don't hit anything, so they get the skybox color. Other rays, they bounce. So when a ray encounters an object, there are actually three color parts that are computed. There's a local color that comes from the Fong illumination model. There is a reflected color, and there is a refracted color. And each of these things can have a weight associated with them. So like, if you look, the checkerboard is not as shiny, is not as reflective as the balls, right? So the local value of the color here is weighted more highly. Maybe it's 80%, and maybe only 20% is the reflected and the refracted. Whereas it's probably the opposite here. These balls do have some local color, right? And obviously a local illumination model is being applied to them because you can see the Fong specular highlight that's calculated by the illumination model, right? But the overall contribution of local is fairly low compared to the reflected component, which is pretty high, which means that these are very mirror-like objects. So a weight that you give for local versus global, local versus reflected and refracted tells you how much, how reflective and refracting your objects are. And obviously, if an object isn't very reflective, you're not going to get much. Oh my God! It's time to be scared. This is showing you how ray tracing works. A ray starts at your eyeball and goes through the screen. Now, as I go through this, keep in mind, all of this work is being dedicated to determine the color of this single pixel. So this process that I'm describing has to be repeated for every friggin' pixel. The whole computation, all it does is set the color of a dot on the screen. So the ray goes through its pixel, and the first thing it hits is this blue ball. I've drawn this as a blue ray to emphasize that it hits a blue sphere. And then there's a reflection and a refraction ray. And the way I set up my recursion, because this is a recursive procedure, is that I follow reflections first. So when I hit this point, there's going to be a reflected ray and a refracted ray. I follow the reflected ray. And it hits another surface that has a reflection and a refraction. Since I'm following reflection first, I then come over here, and of course this was a pinkish ray because it hits the kind of pinkish sphere, and this is a yellow ray because it hits the yellow sphere. And when it hits here, and there's again a reflection and a refraction. So I take the reflection and hit here. Now you might say, well, why didn't you keep going? Well, because recursion, we have to have some ultimate depth that we stop at. And the way I have it set here is we're only going 4 levels deep. So when I get here, I compute a local color, and for my global color, I just set it to black because I'm not going to do a reflection. I'm not going to do any more global. I'm not going to do any reflection or refraction. So I get a local color here that comes back as the recursion unwinds, So I'll have a local color here, a refracted color, and I still have to do the reflective. I have a local color, a reflected color, and I still have to do a refraction ray. And I do the refraction, and it hits the inside, the inside of the sphere. You might say, that doesn't make any sense. They're refraction rays because these are assumed to be like colored glass balls. Think of them as colored, that's Christmas ornaments, colored glass balls, okay? So I get the refraction, and so now I have everything to compute a number, an intensity here. I have its local, I have its reflected value, I have its refracted value. So now that that's computed, it backs up to here, and I can do the refracted ray. So now I have a local color here, I have all of the reflected information. I've got to go and do the recursion for the refracted information. So 6 is my refracted ray. It hits here, and you might say, why are these black? All my refracted rays, I just made them black so that you could tell the refracted rays from the reflected rays. The reflected rays are colored by the sphere that they hit. And the refracted rays, I made them black just so that you could tell that, that they were different. So looking at the image, I can immediately see which are reflected and which are refracted. So here I hit here, and now I'm on the inside of the sphere, so the reflected ray actually will reflect inside the sphere. The refracted ray will actually go outside into the environment here. Well, this guy's not going to hit anything, and so it's not going to contribute anything because it doesn't hit any surface. This guy is going to back up the color of whatever was here. And so that gives us the reflected and a refracted and a local here that can back up and give us a reflected and refract all of the value from this refracted ray. So now then I have a local color, everything I got from the reflected ray, everything I got from the refracted ray. So now I can back that up. So when I get to here, I now have done half the work. I can now have the local color of the blue sphere and all of the global information that came from the reflected ray too. But now I have to do the same process again for the refracted ray. So 9 is refracted, and that splits into 10 is reflected, and that splits into 11 is reflected. I've reached the depth of my recursion, so I back up. I do the refracted ray 12, come back. Now I do the refracted ray 13, the reflected ray 14, and the refracted ray 15. You might say, Mike, I thought you said you were making these things different colors based on what they hit. Why is this one green? Because if I have a reflected ray that doesn't hit anything, I had to give it a color, and I looked around and green was a color that I hadn't used. So this is the green ray here is a reflected ray that doesn't hit anything. I needed to give it a color, so I made green. Okay, and then so all of that unwinds, and when you get back to here, right, you now have the local color, the reflected color, and the refracted color. You'll apply weights to those because some things may be more reflective, some of them may be more refractive, some of them may be not very reflective or refractive. And anyway, all of that comes back to produce a color here. I think it's probably going to be purplish because it's getting the blue here and it's getting the pinkish and the yellow, so it's not going to be just blue. So I made it purplish just because I went, okay, well, okay, all right. Let me finish the recursive part, and then I'll answer. I see some questions have piled up. So what does this look like as far as recursion is concerned? Here's a recursive tree, a recursive call. I'm counting down in my recursion, so my first call has a 4, and I subtract 1 each time, which gives me a 3, and then a 2, and then level 1, and then I roll out, okay, and then come back up again. So, and also notice the rays I follow the reflection path first, so reflection's to the left, refraction is to the right. So you can see, even though you haven't looked at any code yet, you can, in your mind, you can see the recursive structure of this code and how it will work. And eventually, so like ray trace 4 is the local color plus the reflection and the refraction information. And this reflected ray here, it'll hit a surface, and the color of that surface will be some local color plus its reflection and refraction, blah, blah, blah. Finally, you get down to ray trace level 1, you get a local color, and you just return black when you get to level 0, because I'm not going any further. So the global is nothing, it's black. Okay? And we can put this into a little pseudocode. And so here's the high-level pseudocode for implementing recursive ray tracing method. Inputs are some start point and array. Both of those are vectors. And some depth, an integer as to how deep you want to go. And the method returns the color of a pixel. So this would be called over and over for every pixel on the screen, essentially. And as we go through it, I'm not necessarily giving, in the arguments, I'm not necessarily giving you all of the arguments, but I'm giving you enough to make it clear. So you say ray trace, my start point, my ray, my depth. If your depth is 0, in other words, I'm not going to go any lower, I'm at the bottom, just return black. The next thing you have to do is, assuming we weren't at level 0 and just returned already, we're at a non-zero level. So I need to intersect the ray with all of the objects in the environment and find the intersection point, if any, that's closest to the start point of the ray. So I made up the pseudocode thing, right? It says it'll give an intersection that'll be find the closest intersection from the start point of the ray. And we'd have to figure out how to do that, but we need an intersection point for this ray. And we need the closest intersection point. Why do I need the closest intersection point? Well, imagine, if you will, that we have a ray. You can do it real quick. The way I have this here, there aren't any obvious paths, but let's say instead of my eyeball being here, let's say my eyeball had been down here. Well, you'd have a ray that would hit the blue sphere and the yellow sphere. Well, which one do you need to worry about? The closest one, the blue one. So that would be the closest intersection to your eyeball is the one you take, okay? And we don't really know, you've got to check the path of the ray against every object to see if there's an intersection. And if we find more than one intersection, we have to have the closest. So our intersection will be our closest intersection point. If the ray doesn't hit anything, let the color equal the skybox color or the sky dome color, right? So if intersection is empty, then return color skybox color, or I think they call it the sky dome instead of the skybox in Unreal. So okay, now I've got an intersection, so I hit something, and I know I've got the closest intersection. So compute the local color at that point. So I landed on something. Apply the Phong illumination model here, and that'll give me a local color. My reddish sphere, my greenish, or whatever, and this is, so you'll have your ambient and your diffuse and your specular. You'll do all of those calculations that you did before to get the local color. And then you calculate the direction of the reflected ray. We've actually already done something very, very similar to this before, when we had light rays and they hit the surface. And to get specular reflection, we had to calculate a reflection direction. The same computations, which is teeny tiny tweak, because light rays, we assume the vector points at the light source, and now when we're tracing rays, it's in the opposite direction. So you just have to flip a sign. But it's the same equations we've already given before. So that's how we're going to get the reflected direction. Compute the reflected color. Well, how do you get that? Well, you're going to trace ray. This is green because this is a recursive call to the same method. All right. So call trace ray again, but now the start point is going to be the intersection of the previous ray, and the ray won't be the light ray coming from your eyeball. It's going to be the reflected direction. Oh, and don't forget to subtract 1 from your depth as you go into it, because now if this was level 4, this is going to be level 3 going in. All right. Every time you go down a level, you subtract 1, because eventually it's going to be 0 and you're going to return black. Make sense? Okay. So this is going to this is going to generate half the work because this is going to be recursive calls that are going to go down and then they're going to have to float back up to get here, right? But eventually, you'll get a reflected color. So we have a local color and a reflected color, but now we've got to do the same thing for the refracted direction. You've got to compute a refracted ray. We'll have to show you how to do that with the math. And then you compute the refracted color exactly the same way. You're going to trace the ray from the intersection point along the refracted direction. Oh yeah, and don't forget to subtract 1 from your depth again because you're going to go through another recursive spiral. Eventually, though, you'll get back. And when we get back to this level, we now have the local color, the reflected color, and the refracted color. So then combine them together using these weights that I talked about. So your local color will have some weight, your reflected color will have some weight, and your refracted color will have some weight. That'll give you color, and that is what is returned by trace ray, because trace ray, which will be called for every pixel, job is to return the color of that pixel after going through all of the levels of recursion. Okay, so questions. Let me see what you guys have asked so far. So for 1080p, you're casting 2 million, blah, blah, blah. I didn't do the math, but if it's 1080 by what, right? Because you're casting a ray for every pixel, and how many rays does that ray generate? Well, obviously, if you're going 4 levels deep, as we can see here, you could have up to 15 intersection calculations here. Now, it's not always going to be 15. If you notice over here, I have ray 14. Remember ray 14, our little green ray that didn't hit anything? That's him over here. He returns the skybox color because there was no intersection. And, I mean, your refracted ray could have had your reflected ray could have had no intersection. So just because we come here, if there's no intersection, if there's no intersection, the first thing you do in trace ray is you compute an intersection, right? And if there's no intersection, you return skybox color. You don't do any more recursion, right? So even if you're at level, even if the very first ray that came out of your eyeball at level 4 more levels to go down, right? If it doesn't hit anything at all, you just return the skybox color. And so you're not guaranteed that you're going to have 15 intersections. 15 is the most you can have in this setup when I'm going 4 levels deep. So in some places, you're not going to have many intersections. And so those pixels will compute quickly. It's when you get into an area of a dense area of highly reflective or refractive objects that you're going to start having issues, as they say. Is the 4-level limit for the reflections only? No, as I said, they were for reflections and refractions. 4 was an arbitrary number I pulled out of the sky or some orifice. But you probably don't want to go much deeper than 4 because it just gets exponentially expensive every time you go down another level. Let's see. I can see why real-time ray tracing was such a big deal when they started marketing it on the RTX cards. Yes, because it is hellaciously expensive. I can't disregard your question, Stephanie, because I already asked. Answer. Sorry. Let's see. So are you adding black at the bottom because black is 0, 0, 0? Yes, I'm adding black at the bottom because I'm not really adding anything. Black is don't give me anything, right? Don't add any additional color. So that's what black means. Black means nothing, right? Because all of this is we're adding, adding colors here, adding levels of intensity. So black doesn't add anything. So reflection will always have a refraction. The way I showed it, that I could see why you would say that the way that I showed it, but in reality, no, because like look at our checkerboard here. Our checkerboard has reflections. It has no refractions. So this checkerboard object here has I would guess, just looking at it, probably local is 80% and reflection is probably 20% and refraction is 0. Just looking at it, I don't have Hunter's numbers in front of me, but visually that's what that's telling me. It's mainly local color. It's got some global color, and all that global color is reflection. There's nothing underneath the plane, so it wouldn't make any sense to do a refraction off of it. There's nothing that would hit. I hope he didn't implement refraction, because it wouldn't do anything. It would just slow it down. And we can see that here because, like, if, well, the way we have it coded, right, is I don't have any tests around the calculation of the reflected and the refracted ray. In reality, we'll talk about something called adaptive depth control, but in reality, you would probably have a test of some kind here. Well, I say that, but really, we just go one level deep, because let's say that you've got an object that doesn't have there are no optimizations at all in this code, because I'm just showing you the base algorithm. But in reality, you would probably want to check and see whether or not it makes sense to do all of this recursion by checking to look at some function of the weight. Because let's say your refracted weight was 0, well then why in the world would you go through, you know, half the work of the program, going through all those levels of recursion to compute a number that in the end you're going to multiply by 0. So again, this is not optimized in any way. This is just the core algorithm. But in reality, you probably wouldn't want to waste all that work if you're going to end up multiplying it times 0. So that could potentially be 1920 by 1280 by 15 equals 31 million calculations for one frame. Yes, my friend Eric, now you are beginning to understand why. And 1920 by 1080, that's not 4K, is it? Somewhere in here, I think I do the calculation on the next page and talk about why it's so expensive. I don't know, maybe that's somewhere else, but I actually run through the numbers for 4K, and it's ridiculous. It's absolutely, completely ridiculous. And that's for one frame, and Eric wants 144 frames a second. And we got to give Eric what Eric wants, right? So you can see why this is problematic. And also remember, this is we're not implementing a real engine here. We are learning how the algorithms work so that we can program them ourselves. I've got 3 objects in here, and those objects are perfect spheres that have nice little simple mathematical equations to define them, right? This isn't going into a scene with, 10,000 polygons. Oops, right? Because now you suddenly have a lot more objects to test against. And there are ways of controlling that. You have things called bounding volumes. So a lot of times, like if you have some spaceship here, right, you throw a bounding volume around it, a bounding sphere, and so if a ray doesn't intersect the bounding volume, it missed the ship and all 10,000 polygons there, right? And so you only test for individual polygons if you make it through the bounding volumes, and a lot of times you have bounding volumes of various sizes and shapes, so that you can eliminate many of the intersections as quickly as possible. I don't think any of us have the money for a 144 frame per second ray tracing machine here. But this is now, right? And things get faster. So, like I said, you know, high-end games are beginning to play around with limited ray tracing. So, so that's helpful. Also, too, you can get nice effects without totally breaking the bank. Well, here's the trick. Most of the time, the coolest thing that we like out of ray tracing are all those little mirrors, right? If you have a scene that doesn't have glass in it, or doesn't have water that you really want to truly ray trace, then don't do the refracted ray, just do the reflected ray. So if you do that, you can take a calculation that would be exponential and make it linear. So here I've gotten rid of the refractions and I'm just doing the reflections. And so I have 1, 2, 3, 4 intersection calculations as opposed to 15 intersection calculations. So I've dramatically reduced the amount of work. I've turned this into, for 4 levels deep, you'll just have 4 intersections maximum, rather than 4 levels deep having 15 intersections maximum. So now then Eric can do his 1920 by 1080 or whatever it was times 4 rather than times 15. So maybe now you could afford something that would give you that effect, Eric. So this is commonly done, and in fact, this is what we're going to do in our ray tracing program. We're going to say, screw you glass balls. We're just going to do that didn't come out right. We're going to only do reflections. We're not going to do refractions. And you could even get really clever if you had a situation where you had some objects that were reflective and some objects that were refractive, like Hunter probably did, is he probably, for speed, he probably only traced reflected rays. He's a smart dude. He probably only traced reflected rays off of certain objects and refracted rays off the other objects. So you can still keep it to a linear calculation, no more than 4, if you know some properties of your objects and say, oh, this is an object where I need to go down the reflective path. Oh, this is an object where I need to go down the refractive path. So if you did it like that, and you could decide based on the properties of the object which way you went, you would still only go 4 levels deep, right? Or you'd only trace 4 rays if you were going 4 levels deep. So you can choose to get scenes that have both kinds of objects if when you hit the object you decide which ray you're going to follow. But if you want to follow both of them, which you should, right? You got issues. Another thing here too is we'll talk about this, or I'll just introduce it now. It's later in the write-up. But what about shadows? Where did they come from? Well, actually, you need a special ray that we hadn't talked about, a shadow feeler ray. And what happens there is every time you hit a surface, it doesn't matter if it's the checkerboard or if it's the or it's the sphere. When you hit a surface, you create a ray that goes from that surface point to the light source. All right, well, our light's at infinity, so basically from that point, you would check along direction 1, 1, minus 1, that vector, because that's the lighting vector here, and you would see, oh, do I hit an object? If I hit an object, you turn off the diffuse and specular component of your illumination model, because all you get is ambient here. That's why it's darker here, is this is only ambient light and whatever the global component is. So that's how you can get shadows, because you say, oh, is there anything between this point that I'm at and the light source? If there is, turn off everything that's coming from the light source, the diffuse and the specular, and you'll make it darker. But like I said, it's interesting that the shadows of the spheres, you don't see the shadows of their shadows, as it were, because there's nothing in between that point and the light source. Okay, here's something that's obvious, but I'll take a second to say it. You cannot use backface removal. You cannot use backface removal with ray tracing. Why not? Well, because sometimes you see that's what we've been talking about so far. You see reflections of things, so you could easily see the reflection of a back of an object. So if here's our eyeball, right, and I'm showing the rays that hit here along this part of this sphere, you would have a reflection of this sphere, and that's why these aren't blue. That's why these are kind of pinkish, because this is indicating these pixels are the reflection of this sphere and this sphere. So it's kind of some combination of blue and that's not really pink, but blue and whatever the frac that color is, right? I'm seeing the back of this object. So there's no such thing as backface removal. There should never be any such thing as backface removal when you're doing ray tracing. Eric, can you see why this is even more expensive than it appears? Because now, you know, before ray tracing, I could throw away half of my polygons, all of them that weren't facing me, and cut the overall problem that I had in half. But now I can't do that. So if I'm allowing ray tracing in this environment, because there can be mirrors, I can't just throw away the back polygons. I have to keep up with them. Pain, all right? But hey, it looks nice. It looks really nice. That's why we're doing all of this. Okay. So how do we make this happen? Well, I've already given you the core algorithm. What just happened? I think I just crashed. My modem is blinking. Well, if I come back, I come back. Y'all can still hear me, yeah? Somebody say yeah.
Yes, we can still hear you.
Okay, good. And all of you have access to Moodle, so you should have these notes in front of you anyway. So I'm on page 111, 18.2. So all we have to do now is go through all of the math for calculating the intersections. And we'll need to calculate the intersection of a ray with a sphere. We'll need to calculate the intersection of a ray with a plane. We'll need to calculate the reflection vector, which, like I said, we've already pretty much done all the math for that, and a refraction vector. So I go through all my little calculations. I'm looking at my modem, and it looks like it's blinking properly, so I'm going to try to come back. And I'm here. I don't know why I'm doing that in a Dr. Seuss voice, but I am. and no momento. Okay, let me repeat my video, and let me make my video go live. And boom, I'm back. Me and the camera mic. Okay. And we need to share our lecture notes. Again, always keep your lecture notes up in the background just in case I lose video, so we can keep going. So, intersection with ray and sphere, intersection with ray and plane. I go through all the math for the interested student, but we got pretty pictures too. A ray may fail to intersect a sphere. So a ray may go by the sphere and not hit it. A ray may graze the sphere. It may hit right along the edge of it, so there's one intersection point. But more commonly, the ray is either going to miss the sphere, as I showed above, or if it hits it, it's going to hit it in two places, a front and a back. And if that happens, this is the point that we're really interested in, the nearer intersection point. So how are we going to do this? Well, this actually says everything we need to know. We've got a starting point, which originally will be your eyeball, but if we're looking at a reflected or refracted ray, it'll be the intersection point, it'll be the start point. But for the first ray, the start point is our eyeball. We've got a second point, which is a pixel on the screen. And since we've got 2 points, we can compute a vector that is the direction that we're looking at, and I'm calling that vector ijk, or xyz, because I'm already using xyz sub 1 for my eyeball, and xyz sub 2 for the screen pixel. So, if you take x2 minus x1, y2 minus y1, z2 minus z1, that'll give you an xyz. You could normalize it if you wanted to, but that'll be your ijk. So ijk is our ray, our vector. What's a sphere? A sphere is all points that are radius distance away from the center point. So we need to know the center point of the sphere. I'll call that LMN for its XYZ. So LMN is the center point of the sphere. I'll call the distance from the center point to the surface, the radius, I'll call that R. And I'm interested in finding an XYZ, right, along this ray that is R distance away from the center point. You can do that mathematically by coming up with a parametric equation for the ray. By parametric, you'll have a variable t that'll say how long down the ray you want to go. So if I know the direction of this ray and I know how far I'm supposed to go along this ray, call that t, that'll get me any point along this ray. Well, we take the equation, the parametric equation for a line, and we combine it with the parametric equation of the circle, and those two things together, if there are any solutions, x, y, z will give us the intersection point on the ray and the sphere. Okay. So, like I said, here's my ijk calculation. Just subtract x2 minus x1, y2 minus y1, z2 minus z1. That gives us ijk, and here's our parametric equations for the line along the ray. X is your starting point plus your I direction times how far you're going down at t. Same thing in y, same thing in z. So this is the parametric equation using the parameter t that lets us know how far down the line you need to go. We then take and one thing I wanted to show is when we start off, we have to compute ijk. all right, the direction of this first vector from 2 points, our eyeball point and our screen point. After we get an intersection, we'll have a reflection or a refraction direction that we compute, so we will automatically get the IJK because we'll actually have the vector rather than 2 points that we have to figure out the vector from. But anyway, regardless of if we're talking about some reflected or refracted ray, or we're talking about the initial ray, we'll have an IJK, which will be the vector. And so it'll always work the same way regardless. Okay. All right, well that gets us down the ray. What about the equation for a sphere? Well, the center of a sphere is denoted by LMN, right? The radius of that sphere is R. So given any point x, y, z on the surface of the sphere, right, R is x minus L squared plus y minus m squared plus z minus n squared, square root of that. That gives us the distance for any point x, y, z that's on the surface. So squaring both sides, r squared is equal to, gets rid of the square root, or you can take this and set it equal to 0, and this is the equation for the sphere where x, y, and z, when this thing is 0, x, y, and z, the point x, y, z is on the surface of the sphere because it is r units, radius distance away from center point LMN. Okay, so now we've got an equation for x, y, z on the surface of the sphere. I've written the x, y, and z in red, and we've got the equation for a line with x, y, and z, which I write in green here. So if I substitute into my sphere equation, my x, y, z from my line equation. So I'm going to substitute the x, y, and z from the ray traced equations for the x, y, z in the sphere equation. So this red x becomes, well, what is x as far as the line is concerned? This y becomes, okay, what is y in the line equation? This z becomes what is z in the line equation. So now I've got this hairy thing, and I need to solve it. And there's a lot of math that happens, blah blah blah. But eventually, if you multiply everything out, you can get it in the form of a neat quadratic, a times t squared plus b times t plus c equals 0, where a, I've collected all of the terms that are multiplied by t squared. For b, I've collected all of the terms that are multiplied by t. And for c, I've collected all of the terms that aren't multiplied by anybody. And so once I've gotten this, I can then apply the quadratic equation. Boom, minus b plus my square root of b squared minus 4ac over 2a. And I solve that, and t gives me the distance to go down the ray equation to get to the XYZ intersection point. Because remember, the equation for a line, it's a parametric equation for a line, and it's in terms of t is some distance to travel. So now we know the t, right? And from that t and the starting point and the vector for the ray, we can get the XYZ intersection point. Okay, now it's a quadratic, so you get the roots of the equation, and it depends if b squared minus 4ac is less than 0. If this is negative, you don't get a real number, right? So that means there are no real solutions. The line did not hit the sphere. If b squared minus 4ac is 0, well, this equation is plus or minus. If this is 0, plus or minus 0 doesn't change anything. So there's one intersection point, minus b over 2a. And if you get a positive value here, you're going to get two roots of the equation. One will be the nearer intersection point, one will be the further intersection point. So we'll take the smaller t, plug it back into the equation to get the nearer intersection point. And I go through a complete example here. If your math is rusty, a sphere with radius 2, a center point of 5, 4, 10, a trace ray that starts at 0, 0, 0, with the second point, the screen, I guess, at 4, 5, 12. I plug all these numbers in, I drive it through, I do the math. I made a million mistakes when I was doing this because I can't do basic math. And finally, I plugged it into a spreadsheet to get answers that were reliable, because that's how it is for me. It's easier for me to program the equation than to actually try to solve it by hand. And you drive it through, and you end up with a t1 of 1 and the other t of 0.74, 0.74 smaller than 1. So you plug 0.74 back in for t here into the original equation, and boom, 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 you get 3.7, 2.96, and 8.8. So that's the nearest intersection point. Questions about this? There is a chat question. Logan is interested in something that has nothing to do with what I'm talking about right now, which is what language are we doing this in? We're going to be doing it in Python, Logan. But let's concentrate on the math right now, okay? Okay, so that was getting an intersection point for the ray of the sphere. You need to get the intersection point for a ray in the plane. It's a similar kind of deal. You'll have the ray equation. You'll have the plane equation. A plane equation, as we learned going back, is ax plus by plus cz minus capital D equals 0, where D is capital A little a plus capital B little b plus capital C little c. What is all this crap, Mike? A, B, and C is the x, y, z of the surface normal of the plane. So cap A, cap B, cap C is the surface normal. Little a, little b, little c is just some point on the plane. So you need both of those to get D, which is the constant that anchors the plane. The surface normal is just a direction, so it can move anywhere in space. You need a point to anchor it, and that'll give you the plane. So that's what the cap D does. And then XYZ, the little XYZ, is just any point on the plane. Well, any point on the plane, you replace it just like we did before with the definition of X, Y, and Z from the parametric array equations. And that gives us this. You use the math, it's a little bit easier. Here's your T. And there's no squares in there, so there'll just be one intersection point. But here's what it looks like. ABC is the surface normal. Little a, little b, little c is some point on the plane that anchors the plane's orientation in space. You still have exactly the same thing for the line. It's along some vector, ijk, with some starting point, and it'll hit the plane at x, y, z. So that's what you did. You solved this for t. That gave you the t to plug back into your equation to get the intersection point. And because I'm a nice guy, I went through an example with the math. Again, my math skills are terrible, so I had to go back and program it into Excel so that I could get numbers that I could trust. I add when I should subtract. I multiply when I should add. I get my signs. This is what happens when you're dyslexic and you try to do math. That's why I hated math when I was younger. But you plug it in. And that's the reason why I like programming so much, is I find it easy to program in the equations. I just find it hard to actually go through them by hand. What about the reflection vector? These equations look real familiar because we covered them in 16.4.2. These are the equations for taking a lighting vector and computing a reflection vector from a lighting vector. The only difference is our lighting vector pointed towards the light source. Now we're going to be dealing with the traced ray that I'm calling T that points in the opposite direction. So T is like minus L. You still have the same kind of setup here where you've got a ray and you want its reflection. So essentially T, like I said, is minus L. So you plug that into the equation and that flips some signs, but it's the same thing. You could also have in the instance that you graze the sphere, you've got a 90-degree intersection here, and the reflection vector is the same as the trace vector. Is that an R? That's supposed to be a T. That's a T. Okay. It's kind of squiggly, so it looks a little like an R. It's a T. And then you could have a situation like this, where you've got a sphere that hits the back of the plane. This is actually a situation you've got to decide what you want to do. Do you want your planes to be visible both on the outside and the inside? So far, we've always let them be invisible on the inside. So we've built closed polygonal structures. But like if we have a checkerboard, do you want it to vanish if you're looking at it? Do you want to be able to see through it like it's not there if you're below it? Or do you want to still see that it's above you? That's a question you have to decide. But if you do decide to make it reflective on both sides, then you have to take care of this concept that you can have an angle greater than 90 degrees. And so you know, do I just let it pass through to be R prime, or do I have it reflect, which is R double prime? If you're going to have it reflect, you've got to have equations for that. Here they are. Boom. I'll give a full example. And blah, 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 full example. And then I do the refraction. I don't go through I'll do this next time so that we can talk about it. But I just present it. I don't go through a derivation for it. I'm just like, enough of this. Now, the last thing I want to do in our last 2 minutes is show you the assignment. So I put the assignment out on Moodle. We'll talk about it on Monday, but if you want to go ahead and get started, you know pretty much everything you need to know. But what are you going to do? You're going to build one of these scenes, right? Implement a recursive ray tracer outlined in class. Repurpose the Phong illumination model that you wrote for assignment 4 for the local illumination intensity. Implement a red and white checkerboard. We'll have to talk about how are you going to make a plane have a red and white pattern on it. But we'll talk about that next time. Implement 3 highly reflective spheres, 1 red, 1 green, 1 blue. I made them in primaries. That might be a little bit helpful. Define a light source, 45 degrees over your right shoulder, 1, 1, minus 1. You need to normalize that. Center of projection is still 0, 0, minus D. I use 0, 0, minus 500. Optional, for 10 points extra credit, implement a shadowing field array. I'll have to talk about how I've already actually talked about it, but I'll recover shadow field arrays. And optional for fun, see if it's possible to get 144 frames. See if it's possible to move this thing around on your screen in real time. Probably not. Okay, but you could have an animation, right? Even if you can't do it in real time, you could get a frame, capture it, compute the next frame, capture it, and build yourself a little digital movie of the spheres bouncing around. That might look cool. Okay, so that's it. I'll see you guys on Monday. I hope everybody has a good weekend. If you have any questions, I'll stick around here for a few minutes. Take care. Bye-bye.